Okay, so we had our uniform distribution. We had a PDF, we had a CDF, but I find it easier just to count how many options do we want out of the total number of options? Because for a uniform probability distribution, they all have the same chance of happening. But my second favorite distribution is the binomial, the discrete binomial, also called the Bernoulli distribution. But there are a whole lot of Bernoullis. There are at least 5 Bernoullis that did mathematical and statistical things. I believe this is Jacob Bernoulli, but there's a Jacob, a John, a Johann, and 2 Daniels. I gave up trying to keep track of who's who. I'm going to call it binomial because we're really going to categorize everything that could happen into 2 outcomes. Either we get what we want or we don't. So the bi here in binomial means 2 categories. Success versus failure. That's really it. I don't care. I always misspell that. 2 C's. I don't care how many actual outcomes are in each. But if I know when I run this experiment, there's a particular chance of me getting what I want, I'm going to call that the probability of success. And its complement is the probability of failure. Now, this is what bothers me. There's some fixed chance of this happening across the population, which means we're going to give this a Greek letter. And it's a proportion. So the Greek letter we're going to give this is pi. This has nothing to do with 3.14, but it bugs the hell out of me. Just a proportion, p. A lot of textbooks will actually use a lowercase p, but Roman letters go with samples and Greek letters go with populations. So the textbook we're using uses Greek. And that means that the chance of success is this number. That means the chance of failure is 1 minus this number. Whatever this number happens to be, some value between 0 and 1. If I'm thinking about flipping a coin, well then, each of these is 0.5, assuming my coin is fair. If I'm rolling a die and I only call it a success if I get a 4, then the chance of success is 1 in 6. The chance of failure is 5 in 6. Do an inspection. I pick an item out of my line for quality control in my production facility, and I say, this is capable of going out, this passes all the quality control inspections, or it doesn't. Test results. We were talking about a drug test last week. Okay, I either pass the drug test, I come up positive, or I come up negative. The assumption for a binomial distribution is I'm going to run this experiment more than 1 time. So I'm going to do this a lot. It turns out, by the way, that this number is really all I need to describe this entire distribution, because it turns out the expected value of this distribution is exactly pi. And the variance is exactly the product of success times the product of failure, which, by the way, means that my standard deviation is the square root of that. So once I know what this chance of success is on one run of this trial, whatever we're doing, then I can run it more than once. And each of the trials is exactly the same as each of the others. And that means that this number pi, that is my probability of success, is the same every time. Talking about rolling a die. And I said I only get a success if I roll a 4. Anything else is a failure. I'm going to roll this die some number of times. Could be 5 times, could be 30 times. I'm going to call the number of trials n. Because these trials are independent events, I get to just add. So we were talking about rolling a die. What if I tell you I'm going to roll the die 12 times? Success is I rolled a 4. How many times do you think I should succeed? What's your expectation there?
One out of six.
Exactly. 1 out of 6, add it 12 times. That's 12 out of 6. That's 2 times. I just add for each trial I do, right? Now, if I were to roll the die and say success is either a 5 or a 6, well, that changes this proportion, but that's the same each time. So that's still the same setup. By the way, it works for the variance and the standard deviation too. The variance is n pi 1 minus pi. Okay. I've seen this idea before. We built a probability distribution for flipping a coin 3 times. And we built a tree diagram to figure out all the things that could happen, right? But now I can say each of those choices, each of the branches has a weight on them. My chance of success or failure. Because when I flipped the coin, it either was heads or tails. Now I think of each branch as a success or a fail. And I multiply my probabilities going out. This allows me to count the ways and to weight the probabilities. When we were counting our heads and tails, flipping 3 coins, and I asked, how many ways can I get 2 heads? Find that tree diagram. Last week, find that tree diagram for me. Two heads. What we did is we counted all the ways that had 2 heads, and then there were 3 of them, right? Wait a second. Out of 3 coins, I wanted 2 heads. Did I care what order those came up in? That's a combination. And we had a formula for that. N factorial over n minus r factorial, r factorial. In this case, these numbers are small enough, I can actually do these. And there's my three outcomes, right? Think about our trials for a second. I was doing that 12 throws of the die, 12 rolls. And I said, what's the chance I get a certain number of fours? I don't care what order those fours come up in. I just care how many successes I got. And if that's all I care about, then this idea is going to come back. Messing with me. I said I was going to do n trials. Now let's think about the number of successes I can get. I don't care what order those successes come up in. So I'm going to look at all the possible ways to get x of what I want out of n. And then I'm going to multiply by the chance I succeeded. Exactly x times. So that means I multiply by a pi, that proportion, for each success. But I also have to multiply by the failure chance. Because if I succeeded this many times, I failed this many times. This is the probability of getting exactly x successes in n trials. But x can be any number between 0 and n. So I actually have to do this for all the numbers between 0 and n. In our coin flipping, we had, sorry, these are the x values. N was 3 flips. And then we worked out the probability to look like this. So I'm going to write over here, the chance of success was exactly 50% because this was our coin flip. If I change that probability, if I make that bigger than 50%, these numbers should move to be heavier towards the high end. If I make that number less than 50%, then I would expect more low end stuff, right? So this distribution, we could think of this as a histogram, couldn't we? The one I've written is symmetric because our chance is exactly 50%. If my chance is high, the weight should be at the high end, which means it's skew to the low end. If my chance is low, the reverse occurs. There'll be more weight at the low end. It should have a longer tail to the high end. Let's consider an experiment. I don't know what this particular experiment is. I'm going to do it 10 times. There's a chance of success of 0.1. I know. We're picking a phone number out of the phone book at random. What's the chance it ends with a 0? Does your phone number end in 0? Your phone number? Does your phone number end in a 0? It's the last digit of your phone number. The house I lived in before this one. Yeah, it ended in a 0. Okay, clearly. Hey, look at that, 1 out of 10. But if the phone number is chosen at random, well, it could be any digit from 0 through 9. Chance it ends with 0 is 1 out of 10. I like this idea. I run this experiment 10 times. What should I expect? What's the average number of successes I should get? An average doesn't actually have to be a result. I wish I knew where the hell they were drilling. Of course, they're putting a light on the corner of the building. They were doing it the other day at the other building. I'm running it 10 times. I know the proportion. My expected value is 0.1 times 10. I should expect it to happen once. What is the chance that when I run this, I actually get 3 phone numbers that end in a 0? What is the chance that I get x to be equal to 3? I expect this to be a fairly small number. And literally, the formula I need is right there at the top of the screen. Out of 10, I want to have 3 successes. So my chance of success should be raised to the 3rd, and my chance of failure should be raised to the 7th. Now, out comes the calculator. Let's run this number. You could use the formula we were just using on the previous screen. 10 factorial over 10 minus 3 factorial times 3 factorial. Or if you've got a probability submenu, like we do on this calculator, there's my probability menu. I can go directly to the combinations formula. You can do it either way. So on my calculator, it's you put in the first number, you tap the formula, you put in the second number. And there's 10C3, which is a little hard to read because of the glare of the lights. There we go, 120. Which is the same thing you're going to get if you do 10 times 9 times 8 divided by 6. Works out to be exactly the same result. Multiply that by 0.1 raised to the 3rd and multiply by 0.9 raised to the 7th. There's only a 5.7% chance that I get 3 numbers out of 10 that end in a 0. As long as you know 3 numbers, that's all you need. How many times am I running the trial? What's the chance of success on any one trial? And how many successes do I want? That's all I need. Questions?
How do you get the chance of success?
So that's going to be dependent on what the actual experiment is, right? In this case, it was given to me. I was picking a phone number at random, and I was looking at the last digit. Success was it ends in 0. Well, the choices are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0.1 worked. Rolling a die, chance of success. Success was a 4, 1 out of 6. Sometimes I have this information provided to me. We say, I'm looking historically at bumpers on cars. And I know that the chance of a bumper failing a 5-mile-an-hour crash test is 1 in 1,000. There's that. Because they've run the experiment at the National Highway Transportation Safety Administration, I was given that information. A lot of times in the problems I'll be working with, we'll provide that somehow. I watched the ticket counter at the bus station down in Pittsburgh, and I noticed that the number of people who get on the bus with 2 or more bags out of the last 1,000 people was only about 60%. Okay, there's my proportion. If I define 2 bags more or less as success or failure. Absolutely. The textbook provided me with this list as I proceed to drop something. Problem number 17. I was told that we are looking at 9 trials and we're looking at 5 successes, and the chance of success is 0.9. Okay. Should I expect this to be a big number or a small number before I do anything else? What do you think? Why? Okay, wait a second. If the chance of success is 0.9 out of 1, then how many successes should I expect to have happened out of 9 trials? And this number is a lot lower than 8, isn't it? Maybe this won't be very big. Maybe this will actually be a small number because my expectation would be closer to 8 successes. What's the chance I only get 5? That's pretty unlikely. Maybe. Let's run the number and find out. What is my actual probability here? What is the chance that I get 5 successes? I know I want 5 successes. That means I want 4 failures. Yes.
0.
That's actually less than 1%. That is quite a small number. I'm surprised. There are 10 different options for the number of successes. I could have no successes all the way to 9 successes. So there are 10 different options here. And if I really wanted to understand what was going on in this experiment, it might be to my benefit to actually write out all 10 options as a result. All right. The formula is mechanical at this point. I would just have to change this number and this number. The 0.9 and the 1 and this 9 stay the same every time. This is boring. I'm going to cheat. In your textbook, all the way in the back, there's a bunch of appendices. I use mine often enough. I put this little page point on it so that I would be able to find it in a heartbeat. Little brass arrow. Book. There's my other bookmark. This table does exactly that. Somebody went through and beat me to it. And they built the entire list. How many trials did we want? We were doing 9 trials, right? way down here at the bottom. This leftmost column is the number of trials we're doing. And then this second number is the number of successes I'm after. I wanted 5 successes, right? So out of 9, I want 5 successes. It's a whole lot of numbers that come after that. Again, I go back to the top of the page. There's the probability of success. So I wanted 90%. So I need 90%. That's this column right here. Slide all the way down. 9 trials, 5 successes. There's 0.0074. You sneaky mother. As a matter of fact, see these dashes? These dashes mean that those chances are less than 0.0001. They're less than 0.01% likely to happen. We could still work them out, but they're so small that they don't register by comparison to any other things. So if I were actually making the histogram, these first 3 blocks, 9 successes, 9 trials, 0, 1, or 2 successes, all have blanks in them. 3, 4, 5, we ran out of room. Turn the page. 6, 7, 8, 9. And there are the rest of my numbers. Please notice, way up here at 8 successes and 9 successes, we've got some pretty big numbers. That's where most of the weight of this distribution is. Up around 8 or 9 because our expected value, our average, was 8.1. 12 trials at 50%. There's the list. Notice from 0 to 12, top number and the bottom number are the same. Same thing with 1 and 11, 2 and 10. Because if the chance is 50%, this is symmetric. As we move away from 50%, as we get higher, we have a long skew to the left. As we get lower, we have a long skew to the right because the weight shifts towards the low end or the high end. I love this table. I will give you this table for the exam. But please notice the percentages up here, that the chance of success is restricted, right? What if I gave you something with a 63% chance of success? Our die roll was 1 in 6. What's 1 in 6 as a decimal? Which is definitely not in this list, is it? So how would I do that? Well, I could go back to the formula. Or I could cheat a different way. Above the button that says variables right here, I see the word DISTR, distribution. This is a Bernoulli distribution, a binomial distribution. So if I hit that button, second distribution, I have a whole bunch of distributions. The one I don't have here is uniform. That's the one we did on Friday. I'll live with that. But this arrow right here tells me that there's more to this list as I go down. Lo and behold, there's a binomial. I roll the die 12 times. My chance of success is 1 out of 6. I can give it the fraction. And I wanted some number of successes. There you go. We just did, out of 9 trials, a success rate of 0.9. We wanted 5 successes. That's the exact same number you got, Felix, right? There you go. There's a command in Excel that will generate this same thing. In Excel, we use the command binomial distribution. And then we put the number of successes, the number of trials, and the chance of success. However, Excel needs one more piece of information that I haven't bothered with yet. They need to know that I am doing a probability distribution function, a PDF, as opposed to what other option? What other option did I give you for other distributions? There was a PDF and there was a cumulative distribution function. If this is, the last thing is a 0, we use a PDF. If this last thing is a 1, we use a CDF. Now, I have not talked about how the binomial works as a CDF yet. But again, right here in my command under distribution, right under PDF, there's a CDF option. But how would a CDF work?
Yeah, it's like accumulation, so we spend, but then we give the low end to the
Exactly. If I were doing an accumulation, like if I wanted to know what's the chance of less than 5, well, that would be the same as less than or equal to 4. So it would be 0 or 1 or 2 or 3 or 4. Wait a minute, ors. What do I do with probabilities when I see the word or? I add. But then I have to worry about overlap, right? Can I have both 1 success and 2 successes at the same time? These are disjoint events. There's no overlap. Which means if I want to do a CDF, what I'm really looking at is an expression like this. That's a CDF. There is no CDF table. Phooey. But as long as there's a PDF table, I can just count and add up. The function, the actual math involved in writing the CDF version is disgusting. We're not going to do it. I'm always going to do these in the table. Again, if I'm using the same numbers we have here, probability of x less than or equal to 4 is the chance of it being 0 plus the chance of it being 1 plus the chance of it being 2 plus the chance of it being 3 plus the chance of it being 4. And again, assuming I was doing 9 trials at a probability of 0.9, I can go directly to my table and I can look all those numbers up. So, pull up my table. Appendix A in the back of the book. And I say to myself, with a 90% chance of success, these are the numbers I want. Zero, 1, 2, 3, 4. Right there. 3 of those are so small as to count as 0 on this table. So according to this table, there is a 0.09% chance that I will have less than or equal to 4 successes in this particular trial. This is called a compound event as opposed to a simple event. But let's do that on here and double check. If I'm here, instead of using the PDF, I'm going to use the CDF. But notice it's the same setup. I'm doing 9 trials. I want less than or equal to 4 successes. Oh, no, my chance was 0.9. See, that's a p, not a pi. The x value, 4. All right, what the hell does that number mean? I got an answer. I don't know what it means. I'm in trouble. Because 99% of the problem is not doing the math. It's understanding what the hell it told me. What's that answer mean? E minus 4. That's an exponent. That's a power of 10. That's times 10 to the negative 4th scientific notation. 8.9 times 10 to the negative 4th is 1, 2, 3, 4. There's my decimal place. 4 spots over. And if I round that, don't I get 0.009? There we go. So the difference here is that it did in the background all the stuff I did, but it did the actual calculation for each of those 5 options and then added them all up. There is a CDF table. It's not in the book. That's what bothers me. It's not here. I can't just jump to it and find it. But in the source files provided to us in Canvas, here, there's an appendix tables. Please notice this says right on it, Appendix A. There's a CDF in that zip file. If you download that and open it, there'll be Excel sheets for all of these. And then you can just use the Excel command whenever you want, in addition to look it up to confirm it. I'm not sure that's beneficial to doing it on the calculator, but at least there's another option for you. Questions? Talk to me. Top of page 206, there's the summary, the commands in Excel. And down here are some images of what happens as we change that probability behavior. And you'll notice 50% is symmetric. 10%, it's all gathered to the low end, so it's skewed off to the right. 90%, it's all gathered to the right end, so it's skewed to the left. Questions? one of the important things to do is to understand the differences in the words. I'm running 12 trials of whatever this thing is. I say we can have at most 4 successes. I want the probability of at most 4 successes. Which X values am I after? Right. Right. 0, 1, 2, 3, 4. I want at least 8 failures. That's something we haven't talked about yet, is thinking about this in terms of failures. If I say I want at least 8 failures, how many successes am I after? "12 trials. Same setting. Or 2 or 1. It's the same set of X's, isn't it? Different phrasing, same results. Fewer than 5 successes is again the same result, because it says fewer than 5. 5 is not included. So I have to watch, because I'm in a discrete setting. The words fewer, the words at most, the words at least mean I go to the next integer in some cases, but not in others. However, sometimes it's easier to think of the reverse situation. What are the X's that go with this situation? Again, I'm going to use 12 trials. No more than 1, which means I can get 1, but I can also get 0, right? So, if I then asked, what's the probability of more than 1 success? Well, that would be 2 all the way up to 12, wouldn't it? A lot more options. It's a pain in the ass to do this calculation over and over and over and over and over again. So what would be easier, rather than adding 2 and 3 and 4 and 5 and all the probabilities for those? The chance of getting bigger than 1 is 1 minus the chance of getting less than or equal to 1. It is often beneficial to use this sort of flipped perspective, because that's a CDF question, less than or equal to. That's something I can do right out the CDF. So I can do 1 calculation and then just subtract from 1. Even if I'd already worked these out, I had those numbers separately, I could add them and then subtract from 1. In a lot of real scenarios, I'm looking at, did the procedure I just did work or not? Did I succeed or did I fail? As long as I can categorize my outcomes into those 2 broad categories, I succeeded, I didn't. I know the chance of that happening at any 1 trial. I can repeat the process over and over and over. And that works. This is where my house edge comes from at the casino. We were talking about roulette, right? And I said every bet on the roulette wheel had a 2 in 38, a 0.0526 negative expectation. I do that game over and over and over all day long. The more people play, whether or not they win or lose, on average, I take in a nickel for every dollar that gets played. Period. Lots of dollars moving back and forth, whether they win or lose, I'm taking a nickel off everyone. I'm raking it in. Okay. As far as this course is concerned, these are really the only two discrete distributions I want to work with. There are lots of other distributions. I'm not going to cover any of them for two very good reasons, in my opinion. Almost every situation you encounter in real world statistical analysis is working with samples. And when we work with large enough groups of samples, almost every sample distribution is roughly binomial. We'll actually think about this in calculus terms. I won't make you do any calculus, I promise. But what happens as my number of trials gets bigger and bigger and bigger and bigger? What happens if instead of doing 12 trials, I was doing 12,000?
Be dropped off because they're not they're so like minuscule comparatively. And then
So really, my distribution is going to change shape a little, right? And that means what's really going to matter is what that overall central peak kind of thing looks like. In this picture here, helps if I get back to the right page. It'll matter more about what this looks like. We'll have a lot of different categories down here. And instead of looking like separate little histogram bars, they'll all kind of blur together. So instead of looking at discrete random variables, it makes more sense for me to look at continuous variables. And that's where this course technically veers off into calculus. Because the difference between doing stuff that's discrete and doing stuff that's continuous is the difference between doing algebra and doing calculus. We will do no calculus, because somebody will have done it already for me. But that is not today. That is for Wednesday. And unless I'm grossly mistaken, that's the end of what I wanted to cover in chapter 6. And that means that 2 class periods from now, what happens? You turn in another homework assignment for chapter 6 for you. That's Friday. I will see you all then. Have a wonderful rest. Oh, sorry. It's Monday because today is Wednesday. I keep thinking it's the first day of the week. It must be Monday. Today's Wednesday. That's what happens. We have these days off.
Homework for Friday.
The homework is due Monday, not Friday. Monday. I will see you all then. Have a wonderful, I will see you all on Friday, but I'll see you all later. Have a wonderful rest of your day.